First topic, first chapter, states of matter. In this chapter, we're going to be talking about the three states of matter, their properties, and their differences. So there's something we have to stress on here, which is that all states of matter are made up of tiny particles. Now, the way these particles are arranged is different in each one of those three states. So right here we got a crystal. So we're gonna zoom in and we're gonna want to see what is there inside. So we're gonna watch the particles of solids. Particles of solids are arranged in a regular pattern. So if you look closely here, you'll see that the circles which represent the particles are in a regular arrangement. They are very closely packed. There isn't much spaces between those particles. Now, if you heat up the solid, you're going to get the liquid state. The liquid state particles are still closely packed, but those particles are random. So liquids, particles are closely packed, random, and they could actually move slightly past each other. So the movement in liquids is very limited. It's just limited to sliding between those liquid particles. While the movement in solids is quite different because solid particles cannot really move. They could just vibrate around their fixed positions. Now, if we heat up the liquid, we're going to end up with a gas. In the gas phase, we got particles randomly arranged, just like liquid, but the spaces between the particles is really large and they are free to move. The particles in liquids are actually free to move. So once again, if it's a solid, then the particles are closely packed, there isn't much spaces between the particles, and they're arranged in a regular pattern. That's the motion in solids. The motion in solids is just limited to vibrations. If you go to liquids, then you got particles are closely packed, but the movement is more of sliding. The particles are sliding past each other and they're still closely packed. In gases, the particles are far apart and they are free to move. I want to take a look at properties of the three states of matter. So first, I want to look at their ability to be pressurized. So I will compress solid, liquids, and gases in these syringes, and I want to see how are they going to behave under pressure. So from here, I could see that the solid wasn't able to be compressed. Not even the liquid was able to be compressed, but the gas was compressed, it was squashed, right? This is because gases got plenty of space between their particles. So again, in terms of compression, the only state that is able to be compressed is actually gases. We're going to take a look at their shape. Now, in terms of shape, solids got fixed shape and fixed volume. So solids don't change their shape, not even their volume, because the particles are very well attracted to each other. Now, liquids, on the other hand, have fixed volume, but their shape is not fixed. The shape of a liquid is always the shape of its container. So if this liquid was placed in a beaker, it will look like a beaker. If it's placed in a jar, it will look like a jar. So, however, the volume, if I've had inside this liquid, if I've had 25 centimeter cubed of this liquid, then it's not going to actually change. So 25 will always be 25. So volume of liquids does not really change. Now moving on to gases, gases don't have fixed shape and don't have a fixed volume. So the volume of a gas will always be as much as the space that you put it in. So if you put a gas into a room, it will occupy the entire room. Now, there's one more property, which is their ability to diffuse. What is diffusion? Diffusion is like the ability of particle to spread out. Now, since solid particles are closely packed and very well attracted to each other, then there is no way that these particles will diffuse. Liquids do actually spread out. So if you put a drop of ink into water, you'll see that the ink actually is spreading. So this means that liquids actually spread. Gases diffuse even better than liquids because the attraction between gas particles is really weak so that they could diffuse very easily. In terms of density, now density is like how much particles you got per volume. Now, since solid particles are very well attracted and they're very closely packed, then they're actually going to be denser than the other two states. So solids are usually denser than liquids and gases. Some liquids like oil actually have low density, so they could float on the surface of water. Gases got to have the lowest density because the particles are spread about, right? So they're far away from each other. So they are the least dense among the three states of matter. This table is taken from my textbook. It shows you all properties of the three states of matter, and it shows you one really important line here, which is about their forces of attraction. So solids have very strong forces of attraction. You could see here that force of attraction in solids is the strongest. Now, this line will really help me to figure out or to explain all of the properties. So for instance, if they've asked you, why is it that solids don't diffuse? You're gonna have to say, forces of attraction in solids are actually strong, so particles are not free to move. On the other hand, if they've said like, why is it that gases can actually diffuse? You're gonna have to say, they have very weak forces of attraction, and that's why gases can actually easily diffuse. We're now going to practice the properties of matter. So I'm gonna have to put each one of these properties in the right box. So can be squashed easily. That's gases because they could compress them. Flows to fill up the entire space. Again, it's gases. They have fixed shape, so they don't change their shape at all. That only applies to solid. Diffusion could apply to liquids or gases, so it could be either. And expands to fill up all available space. This is for gases. If you've been choosing low density, that's liquids, will not spread out at all, that's solid. The one that has the highest density, again it's solid, cannot be compressed, that's liquids and gases. So I have more of these here, so you could pause the screen and try to choose whether it's solid, liquid, or gases for each one of those properties. So they can be compressed, therefore it's going to have to be gases. It's gas here. They take up the shape of their container and cause some pressure. So since they've said they just cause little pressure, then I choose liquids because gases can really exert way more pressure. We're going to get to gases, we're going to get to pressure later on in this lesson. They have no fixed volume, so that's only for gases. Gases change their shape and volume. The only one that has fixed shape is solids. They cannot diffuse. That's again only solids. They have flow density is, again, it's gases. It could also be liquids, but it's relative. We're going to look at changes of state. So if you've heated like a piece of solids, like ice, then obviously the ice is going to turn to liquid. If you keep on heating, then it's going to turn to a gas. So particles, when they're heated, they actually gain heat energy. this heat energy is going to get converted into motion. So the particles move faster, and due to their fast motion, they could actually overcome those forces of attraction. They win against those forces of attraction and they change their state. So you could go from one state to another by heating or cooling. So for instance, freezing requires you to cool down the liquid. So melting, on the other hand, needs heating. So melting is a change from solid to liquid. Boiling also requires heating. So if you could boil a liquid, you turn it to a gas. I think I have to switch this one here. Condensation is a change that requires cooling. So these are the 4 changes of state. You have to be familiar with these terms here. Now, as I've said, there are changes that require heating and there are other changes that require cooling. So if you go in this direction, so left to right, these changes all require you to apply heat. That's why those changes are called endothermic. So endothermic. An endothermic change is the one that requires you to apply the heat. Going the opposite direction requires you to cool down. It's the opposite. We call it exothermic. So just think about it. If this change requires applying heat, it's endothermic. If it's the other way around, then it's exothermic. Here I'm going to solve a question about properties of matter. So in this question, what they want, they said compare the movement and the arrangement in solid nitrogen compared to gaseous nitrogen. So again, the comparison here is solid versus gas, but they want us to compare 2 things. They want us to compare movement and arrangement. So I'll start with solids. Solids particles. Now, first I'll start with their movement. The motion in solids is only vibration. So solid particles only vibrate. Now I need to turn to their arrangement. So I say solid particles. Now you remember how they're arranged. They're arranged in a regular pattern, or arranged regularly. Now, if you are to turn to gases, gas particles are actually free to move. So gas particles are free to move. Moreover, need to still to talk about their arrangement, and they are randomly arranged. So obviously this is not the neatest way to answer questions, but you will always have access to those answers. They're written based on the marking scheme, so you don't need to worry about copying in the class or something. There's one new change, also the last change of state. This change of state occurs only to few types of materials. One of them is iodine. Iodine is like a black solid. If you heated it up, then it turns straight into a gas. So you don't get into liquid iodine. There's no liquid iodine. So again, it turns solid to gas. If you cool it down, you return back gas to solid. This change of state is called sublimation. So sublimation, if you want to define it, it's to change a solid to gas or the other way around. Again, this only applies to few substances. One of them is iodine. The other one is carbon. So there's this is taken again from the book. It shows you all changes of state, including sublimation. Now, you do get a lot of graphs about change of state. This kind of graph where you go from solid to gas, we call this a heating graph. Now, there's something special about the graph. What's really special here is that it's not like a steady increase, because you do have two parts where there's no actually change in temperature. There is like the temperature stays steady. So whenever you have like a change of state, so for instance, whenever we're going from solid to liquid, melting, temperature remains constant. Same applies if you're going to freeze something. So the temperature remains constant as long as there's a change of state taking place. Once you turn to the liquid, then the temperature starts to rise again. So this kind of graph, as we've said, it's a heating graph. That's a cooling graph. Now you could see, because we're going from gas, then we're ending up with a solid. So that's the liquid, just because of the way the particles are arranged. That's the gas. And a change from gas to liquid is called condensation, remind you. Solid is the end here, and that's the liquid to solid, which is called freezing. So again, generally speaking, if you mixed up two things in chemistry and you found that the temperature is rising, like here, they've added some magnesium to an acid, and they found that temperature is rising, this kind of change is called exothermic, just like what we've seen with condensation or freezing. If you mixed up two things and the temperature drops, like here, I'm going to add this solid to the water, and the water becomes really cold here. This kind of change is endothermic. So endothermic changes are always, there's always a change in temperature. So here, for instance, we went from 20 at the beginning to 4. So you just need to know those two terms, and you need to know where to apply them. So for instance, if you've seen this rise in temperature, there is exothermic. Seeing temperature is dropping, then it's endothermic. We're going to have more about these exothermic, endothermic changes later on when we take the lesson about energetics. Right now, I want really to focus on this heating and cooling curves. So right here I have the 3 states of matter. You could tell by their motion, sliding, vibration, free to moving gas, and you could also tell by their arrangement. Now, let's take a look at some heating curve. So I have a cube of ice. I'm gonna heat it up. Take a look at the curve here. The line increased, but then it became steady. Once you see the line is becoming steady like this, this means there's a change of state, and that's shown here. You could see that it's turning now into a liquid. Once you turn completely into a liquid, then you see that the temperature is rising again. So as long as there is a change of state, you will find that the line or the heating curve becomes steady. You're going to have now another steady state or no rise in temperature, and that's when the liquid starts to evaporate. So from any curve, you should be able to tell the 3 states of matter, and you should be able to tell when is the change of state is happening. You can also tell what is exactly like the melting point. So for instance, here in this graph, you could see that the melting temperature is 0. That's because this is the point where the line became steady. You can also tell that the boiling temperature is 100, because that's when the line again became steady. So these particular melting boiling points are specifically for pure water. So if you have pure water, then the boiling point is going to be 100 and the melting point is going to be 0. If it wasn't really pure water, then the boiling point will actually rise, but the melting point will drop. We'll talk more about these in the next class. So once again, there are changes here that are endothermic, just like melting, just like evaporation. You have changes that are exothermic. Just think, ask yourself, whenever you are to decide if it's endothermic or if it's exothermic, ask yourself this question. Am I heating to cause this change? Like if you have a piece of chocolate, you need to heat it to melt it, so it's endothermic, right? If you have water and you're freezing it, you're not really heating here, you're cooling, so that's why it's exothermic. We'll talk about pressure. Now, pressure only applies to liquids and gases. Solids, because they're closely packed, they cannot really exert pressure. So particles of a gas inside the balloon that are continuously colliding with each other, but they're also hitting the wall of the container, which is the balloon in this case. The more they hit the balloon, the more they hit the wall, the higher the pressure is. You can increase the pressure here by increasing temperature, because when particles are heated, they gain what we call heat energy. This heat energy turns to motion. Motion here is called kinetic energy. And with more motion and kinetic energy, then the pressure will rise, because those particles are just hitting and hitting the wall of the container. Now, here's a question about pressure. They said, why the pressure inside the container increases when the temperature is increased? So what does pressure have to do with temperature? So again, what do you say here? You say that higher temperature, you're going to have to write neatly in the exam, increases what we call kinetic energy. Now, when kinetic energy is more, then you get more what we call collisions. Not any collisions, collisions with the wall of the container, because that's what really is pressure is all about. So one more time, if you're heating, then you cause more kinetic energy. With more kinetic energy, you get more collisions with the wall of the container. Now, how do we know that about particles? So where did we get this idea that everything is made up of particles? There's one very simple experiment, which is the case when you have dust in a dark room. So you have a dark room, there's like a ray of light coming from the window. You see that the dust particles are moving randomly. This random motion of those dust particles has to do with particles, because the only reason why they're moving randomly is because they are hitting the air particles. You don't see air particles because they're small, but they do exist because the dust particles, they're continuously hitting those air particles and they're changing their direction. So the reason why these dust or smoke particles always move randomly is because of what we call Brownian motion. So this motion is called Brownian after the scientist who first found it, which is all about gas particles hitting the smoke and causing them to move in a random motion, just like this. Another evidence of particles and matter is from diffusion. We've seen diffusion earlier, which is like spreading of particles. Like here, the left side has plenty of particles, so we call this area of high concentration. If you let those particles spread, then they will move randomly until we get to a point where I have like more or less equal number of particles on both sides. So what I say in this moment, I say, well, there isn't any net movement of particles left to right because they're mostly equal. we could study the effect of temperature on diffusion. So right here I have 3 beakers. Now you have a cool beaker, there's a moderate beaker in the middle, and there is a hot beaker on the right. I'm gonna put solids, crystals, inside these beakers of water. The first thing that's gonna happen is that the solid will dissolve. When it dissolves, it will turn into the liquid phase. So again, you don't have any diffusion as long as it is in the solid state. So first of all, we'll have dissolving. When it's dissolved, then it starts to diffuse. Now, keep an eye on the 3 beakers, because the hot beaker, the one on the right, is the one that diffuses most rapidly. The one on the left is going to diffuse slowly. Now, the reason why it's diffusing slowly is because it's low temperature. When the temperature is low, particles don't have much kinetic energy. They cannot move rapidly. So again, eventually we will reach a point where we will have equal diffusion, but nonetheless, the hotter or the higher the temperature, the faster the diffusion is. There's another experiment here which is also about diffusion. This experiment is particularly important. So what do I have here? I have some piece of cotton soaked in ammonia, and I have another piece of cotton that is soaked in hydrochloric acid. Now I'm gonna put both pieces of cotton inside this tube after that I've soaked them into their liquids. Once I place them inside the tube, right, so gases will diffuse from right to left and left to right. What we really need to study here is like which gas is gonna diffuse faster. Now the answer is depending on like how heavy is each one of those gases. So again, this gas right here is called NH3, and this gas right here is called HCl. We'll get to those formulas later on when we study more of chemical formulas. But right now, I just want to show you how to work out the mass of any molecule. So for instance, NH3, you need to get to the periodic table. You'll get the periodic table like everywhere, even in the exam. And you check the mass of a nitrogen. So the mass of one N is 14. The mass of one hydrogen is just 1. So therefore, the mass of NH3 is going to be 14 plus 1 times 3, because there are 3 hydrogens, and it becomes 17. HCl, the mass of one chlorine in Cl in the periodic table is a lot. It's like 35.5. Now, so the mass of HCl is going to be way heavier. So HCl is going to be 1 plus 35.5 is going to be 36.5, and that's way more mass. So conclusion is like, this gas is heavier than this gas. So who do you expect to diffuse faster? The one that will diffuse faster is the one that is lighter. So again, lighter things move faster. Here I have ammonia on the left. It's going to diffuse fast. It's going to run left to right. And they're going to meet up right closer to the HCl. So you will see, you've done this experiment, you will see there is white smoke forming closer to the HCl. Again, it's going to be closer to the HCl because this is only going to move shortly because it's way too heavy, and it's going to move much faster. So they will hit out each other and they will form like white smoke, which is a sign that they have actually reacted. We're going to look at a question, paper 4 question about diffusion. So I was given here 3 gases. Now each one of these gases is different. There's nitrogen twice and there is chlorine. And they've been put at different temperatures, right? And they're showing me here on the right, they're showing us the rate of diffusion. So you could see that the one that's really diffusing really fast is nitrogen, and it's at 50. So we've seen this already today, that higher temperature means faster diffusion. But I do also see something else here. I see that chlorine is diffusing really slowly. Now, this has to do with the mass of chlorine. Chlorine is a heavier gas than nitrogen. So you refer to the periodic table, you find that the mass of chlorine is 35.5. The mass of nitrogen is just 14. So it's like way heavier than nitrogen. So first question, explain why nitrogen gas diffuses faster than chlorine. You have to simply say that chlorine has higher molecular, it's like a mass of a molecule, molecular mass, and the higher the molecular mass, then the slower the diffusion is. Then they said, explain why nitrogen diffuses faster at higher temperature. We've seen similar question today. You say higher temperature results in what? Results in more motion, we call it kinetic energy, and that causes diffusion to happen faster. So one more time, nitrogen has lower molecular mass, or chlorine has higher, then it diffuses faster than chlorine. Now they've given me this diagram, and it's more or less same as the experiment we've seen today, but they flipped it. They put hydrochloric acid on the left and ammonia on the right. They've given me the formulas here on top. They said ammonia is NH3, hydrochloric acid is HCl. They are asking me a question. They said, where will those two gases meet up? So where will their reaction occur? We've seen today that they will actually diffuse, but they will meet up always closer to the gas that is heavier. So since HCl is a heavier gas than NH3, it's given me the formulas here, therefore they're going to have to meet closer to the heavier gas. There are more questions. They said name the process, so the name is diffusion. Then they've said where will they meet? They say they meet up at A. Reason, this is because ammonia diffuses faster, or you could say hydrochloric acid or HCl diffuses slowly. It has to do with their mass. Finally, they said predict the results. Sorry, I'll just go back. Predict how the results would be different if you've had it at higher temperature. So what would you expect to see if the same experiment was done at a higher temperature? We already know that the higher the temperature, the faster the diffusion. So if the same experiment has happened at higher temperature, then you expect the result to appear much faster. So you'll get to see the smoke that forms between those two gases much faster if the temperature was higher. So again, here's the answer. The solid will form faster. That's because higher temperature gives more kinetic energy. So that was all for today. This means we're done with the first topic. We've completed the first topic about the states of matter. The next topic is going to be called the methods of separation, or you could call it separation techniques. That's the next chapter in this chemistry syllabus.